a process which is a bit foreign to most. It has to do with the fact that temperatures in the atmosphere can change and change dramatically without adding any heat to the atmosphere. And all that happens because as you move air up and down the atmosphere, it expands. Pressure is much higher near the ground, and as you take a volume of air and move it upwards like a balloon, it's going to expand in size. And that process of expansion as it rises takes energy, which causes the temperature to drop. So we're going to talk about this adiabatic process, adiabatic, that is without the addition of heat, is what we're talking about here today. There are some key points I want you to start with. First is we're going to talk about 3 different adiabatic lapse rates. Let me back up and talk about lapse rate. The lapse rate is defined as the rate at which temperature decreases with altitude. The rate at which temperature decreases. We expect temperature to decrease with altitude. The ground is being heated by the sun, and as you move away from the ground, typically temperatures drop. So a positive lapse rate means that the temperature is dropping with altitude, which is a bit counterintuitive. First, I'm going to describe something called the dry adiabatic lapse rate. This is about 10 degrees per kilometer. So if you take any air in the atmosphere and you cause it to rise up a kilometer, it will be 10 degrees centigrade colder when you get there. If the atmosphere is dry, and by dry we mean it's not saturated. So humidity, relative humidity is less than 100%. You take the air, start lifting it, it's got to cool. It has to cool at that rate of 10 degrees per kilometer. And this graph illustrates that we might start with an air parcel at 30 degrees at the surface. You cause it to rise 1 kilometer, 1,000 meters. It's going to be dropping to 20 degrees, and then 10 degrees if you go to 2,000 meters. This is why the tops of mountains are often colder than down the bottoms of the mountains. It's all to do with the fact of this adiabatic process. Air expanding takes energy. I mean, think about it this way. If you're playing pool and hitting the ball against the ball pretty much comes off the wall at the same speed it hits the wall. Imagine playing pool on a billiard table that's expanding as you play. That ball hits the side and it's going to come off at a much slower speed than it hit. That's the energy. It represents the loss of energy because of expansion, and that causes a lowering of the temperature as you lift the air higher and higher in the atmosphere. Likewise, you cause the air to come down to the ground, it's going to warm. So importantly, rising air cools, sinking air warms. And we know this happens in our atmosphere. As the air parcel is lifted, it takes work to expand the air parcel, causing a decrease in temperature. If the air isn't saturated, it's going to cool at the 10 degrees per kilometer, and you must remember that number. It's actually not 10 degrees, but for the purpose of this class, that's fine. This is called the dry adiabatic lapse rate. On the other hand, if the air is saturated, if the relative humidity is 100%, and you start lifting the air up, what's going to happen is that, yes, the air is going to try to cool, but because the temperature is dropping and you can't squeeze any more moisture into the air at the colder temperature, some of that moisture is going to then be condensed into clouds. And that process of condensation actually releases heat. So the rate at which the air temperature will drop with altitude then is not as fast, because there's extra heat being added as you lift the air up from the condensation. That extra heat means that the lapse rate is going to be somewhere around 6 degrees per kilometer. So far I've asked you to memorize 2 numbers. Air is dry, it's going to cool at 10 degrees per kilometer. Air is saturated, it's going to cool at 6 degrees per kilometer. This is called the moist adiabatic lapse rate. Now, we're going to say it's 6 degrees per kilometer, but please understand your mileage will vary depending upon how moist the atmosphere is. And this table 5.1 I'm showing you here shows that depending on the temperature and what pressure you're at, the moist adiabatic lapse rate in reality can be different than 6. For the purposes of this class, 6 is a dandy number. and that's all I'll ever expect you to know. So let's test if you understand what I've been talking about so far. The temperature outside. Before I pose this question to you, there's one more fact I need to tell you, and that is the dew point also changes with altitude like temperature does, but it changes at a rate of 2 degrees per kilometer. Let's review that much. 10 degrees if it's dry, 6 degrees if the atmosphere is saturated. Regardless, the dew point temperature changes at 2 degrees per kilometer. Knowing those three numbers, now I challenge you here. If the temperature is 20 degrees and the dew point is 8 degrees, what would they be if you lifted the air by 1 kilometer? What would the temperature and the dew point be if you lifted the air by 1 kilometer? And you have 5 choices here you can choose from. I'll give you a moment to consider that question. And let's look at the results. It looks like we have people changing their votes is what we have going on here. But the correct answer is C. The temperature would be 10 degrees and the dew point would be 6 because we've lifted the air by 1 kilometer. Temperature is not saturated. The temperature is 20, the dew point is 8, so it's not saturated. Saturation would mean they're exactly this dew point equals temperature. So by lifting it by 1 kilometer, the temperature is dropped by 10 degrees to 10. The dew point would have dropped by 2 degrees to 6. And it would make choice C the correct answer, as you cheaters are now changing your votes to that answer. All right. Let's go on to the next slide. So this is let's make it a little bit harder here. Let's see if I remember what next. Oh, before I ask you this question, there's a third thing I need you to know, and that's something called the environmental lapse rate. The environmental lapse rate is reality. Please understand that the dry adiabatic lapse rate, the moist adiabatic lapse rate are both theoretical lapse rates, the rate at which air should change as you move it up and down in the atmosphere. But the reality is twice a day we send balloons up from many places around the world and we measure what the actual lapse rate is. And the actual lapse rate we call the environmental lapse rate, the rate at which temperature changes with altitude. And that's going to be affected by many things. Maybe the air is moving up and down, and if it is, it's got to change temperature at the dry or moist adiabatic lapse rate. But air may not be moving vertically, and it's possible that the air near the ground is coming from the southeast, and air in the middle of the atmosphere is coming from the west, and air at the highest altitude is coming from the north. And so you're just mixing a bunch of air together. You're going to wind up with an environmental lapse rate that's just all over the place. But this is what determines the stability of the atmosphere, and we'll talk about that. The stability of the atmosphere is determined by what the environmental lapse rate, how the environmental lapse rate is compared to the dry and or moist adiabatic lapse rate. So, on this graph we're showing that if the measure of stability, that is the measure of lapse rate outside, we send the balloon up, and if your lapse rate is small, that would be represented on this graph by, small meaning the lapse rate is not changing, is not dropping very fast with altitude, your air is extremely stable. If the lapse rate we measured it very fast, so temperature is dropping rapidly with altitude, it'd be on the left side of this graph, and it indicates the atmosphere is absolutely unstable. So as a rule of thumb, the walk away here is if the temperature is dropping rapidly with altitude, the air is unstable. If it's dropping slowly with altitude or even increasing with altitude, we call that an inversion, then the air is extremely stable. So anything we can do in the atmosphere that makes the lapse rate become steeper makes the air less stable. Think about that for a second. Things that might make the lapse rate become steeper and what those could be. And I ask the question of you now, which of these lapse rates I'm presenting to you here is the least stable? 8 degrees per kilometer, 4, 0, 12, or minus 4 degrees C per kilometer. Which of them is the least stable? I'll give you a moment to answer that question. And while we do that, let me just check to see if you've asked any questions. Can I go over the lapse rate again? Just understand the lapse rate is the rate at which temperature decreases with altitude. The rate at which temperature decreases with altitude. Are there other things that affect the environmental lapse rate? There are so many things that affect the environmental lapse rate. That's, we'll be talking about those for a number of weeks in the course here. Today, let's just focus on the lapse rate, the adiabatic lapse rate. What color are the balloons we send up? Those are multicolored. Multicolored. And you do need to know the humidity. This is a good point here. Do we need to know the humidity? Yes, you do. In order to know whether the air is going to be changing at the moist or the dry adiabatic lapse rate. All right, let's see how your votes are coming in here. I see. So you rearrange your list. And the least stable is, in fact, going to be that with the greatest lapse rate. So I can see that most of you got them right. Excellent. 8 degrees per kilometer is the correct answer, and the order in which they should be ordered here goes from the largest number to the smallest number. In fact, minus 4 degrees per kilometer indicates an inversion. You probably know that inversions are associated with air pollution. If temperature is increasing with altitude, it becomes very difficult for the air to move vertically. So whatever you put in the air is pretty much going to stay in the air at the altitude you put it. So the more stable the atmosphere is, the greater the chance for air quality issues. The higher the rate of lapse rate, the greater the chance then for convection. That's what we need to understand here. There are a variety of ways, and just back up for a second and point out that air does not like to move vertically. It's extremely comfortable being at whatever altitude it's at because it's in a strong balance between gravity pulling it towards the ground and something we call the pressure gradient force, which is pulling it towards outer space. Outer space has basically zero pressure. So air always wants to go to where pressure is lower, from high pressure to low pressure. So air is trying to get sucked out into space in one way and being pulled by gravity the other way. And that balance, called the hydrostatic balance, keeps air at one altitude. And it doesn't want to move from that altitude. So it's going to take something special to make the air actually move up and down. And here are 4 possibilities, ways that you can force air to move up and down. First of all, uneven heating of the ground. You heat one spot, maybe it's made out of asphalt like a city, and another spot is maybe a lake, so it's much cooler. That causes uneven heating, and that can cause the air to become unstable over the city, and you can get some convection. The second is just take the air and slam it into a mountain. It has no choice but to go up. And in that case, you can form clouds over mountains, and those people who live or vacation near mountains understand that convection often happens in the afternoon because of this forced air up the mountain. You can get convergence of air. Famously, Florida is a peninsula surrounded by water. Air is flowing onshore from both sides of Florida, converges in the center. Air is rising in the middle of Florida, and Florida becomes the most popular state for thunderstorms in the country. And lastly, fronts. You'll hear about cold fronts and warm fronts and such. These are demarcations between different air masses. Some are heavier than others, and you get a heavy air mass pushing a light air mass out of the way. That will cause the air to rise. So at least 4 different ways we can force air to move vertically, but typically it doesn't want to. So let's consider that we do, in fact, take air and force it into a mountain. And we're now going to start thinking about, given some initial conditions, how does that change the quality of the air, the characteristics of the air as we move up over the mountain. So here's a situation, and I've drawn a perfectly triangular mountain of 3,000 meters high. And we're going to start with air on the upwind side, which is the left side. Air is flowing from left to right in this picture. And the temperature is 18 degrees centigrade coming at the mountain, and dew point is 6 degrees. All right. This is the example I want you to consider. And I'm give you a minute for this because this is a challenge at this point. Starting at 18 degrees centigrade and 6 degrees for the dew point, where would you expect the cloud to form? Now, to do this, answer this question, I suggest you go about it in maybe 500 meter increments. What would the temperature be when you got to 500 meters? What would the temperature be then when you got to 1,000 meters? What would the dew point be in those two cases? And you're going to take the air and move it up in 500 meter increments until you get to that place where the temperature equals the dew point. And at that moment, that's where the cloud forms. This is how you predict how high in the mountain you're going to have to climb before you're into cloud. You can go through that little calculation. I'll give you a moment or two to do that. And I'm sure, I see many of you are confused by this concept. That's not surprising. But I ask you anyway to try to do this calculation. You're starting at 18 degrees centigrade with a dew point of 6. How high in the mountain do you need to go before you start seeing a cloud? And I'm seeing quite a few dots on the map here, everything from roughly 1,000 meters all the way up to roughly 2,500 meters, so there's clearly some discrepancy here. This would be a good time to turn to your neighbor and defend your answer with one another. But today we're just going to go straight ahead and talk about the process, about how you would answer this kind of question. And let me move forward, where I go through the steps here. 18 degrees at the surface, 6 degrees centigrade. You get to 500 meters, it's going to be 5 degrees colder because it's 10 degrees per kilometer. The air is not saturated. Temperature is not equal to dew point yet. So you're cooling at the dry adiabatic lapse rate. The dew point changes at 2 degrees per kilometer, so for half a kilometer, 1 degree. And you'd be down to 13 and 5. By 1,000 meters, you'd be down to 8 degrees and 4. And at 1,500 meters, the temperature now would equal the dew point. That's the place the cloud forms. Things I've not told you yet. First, at that point, now you're at 1,500 meters, the temperature is equal to dew point. Now you're going to cool the rest of the way up the mountain at the moist adiabatic lapse rate because you're saturated. So you're going to now cool at 6 degrees per kilometer, and the dew point is going to change at the same rate. Once you're in the cloud, the dew point can never be greater than the temperature. I'll say it again. The dew point can never be greater than the temperature. So we're already at 3 degrees. If we go to 2,000 meters, now the temperature is to 0. The dew point's at 0. By the top of the mountain, we're down to minus 6 degrees centigrade. Dew point is also at minus 6 degrees. You're in cloud all the way from 1,500 meters to the top of the mountain. I'm hoping that makes sense. But as we go down the other side of the mountain, the second we go over the top of the mountain, we start down the other side, the air starts to warm up by the adiabatic process. But we're not adding any more moisture to the air. So the moment we start going over the mountain, the we're going to be warming at the dry adiabatic lapse rate going down the mountain. And we start at -6 degrees for the temperature and -6 for the dew point. And as we move down the mountain, the temperature is going to be rising at 10 degrees per kilometer. The dew point is going to be rising at now 2 degrees per kilometer. And what happens by the time we get to the bottom here, as the temperature is up to 24 degrees centigrade with a dew point near 0. So what's happened by forcing the air over the mountain is you systematically have taken air and made it both warmer and drier because of the adiabatic process. Warmer and drier as you move over the mountain. And those of you who have ever visited the state of Washington, for example, or Oregon, appreciate that on the west side of the Cascades, which look a lot like this, it's much moisture. Seattle is famous for being drizzly and damp. But if you go across the mountains into eastern Washington, it's quite dry, excellent vineyards in that area, drier conditions, and warmer conditions, all because of this adiabatic process. Finally today, based on what we've talked about, what upwind conditions would lead to the greatest rise in temperature from upwind to downwind of the mountain? What conditions of temperature and dew point on the upwind side, the left side, would produce the greatest warming as you move across the mountain? And I'd like you to type some thoughts here about what kinds of conditions would, so let's say Seattle. What air in Seattle would produce the warmest temperatures to the east of the Cascades? I'll give you a moment to consider that. And as you do that, I'll just check your questions you're doing here. Oops. Can dew point ever equal temperature? Yes, it certainly will, and that's the point at which temperatures form. And thank you for sharing a link here about that in Wikipedia. Can I explain air masses in more detail? I'm going to have a whole other lecture on that topic, so I'll hold off on that. Does air move vertically? It can move vertically, but as I say, it takes special conditions. Thunderstorms are really quite a unique process because to get that kind of vertical motion, the atmosphere requires a whole set of conditions that just don't normally exist in the atmosphere. All right. Let's come back and see some of your answers. Confused, I hear you. Increased moisture in the air. I guess I'm looking for as an answer that might include something more specific than that. Remember, if I ask this kind of question on an exam, I would be looking for an answer that's fairly complete and uses words like temperature and dew point, as that's what we've been talking about. Cute cows, that's a good one. No idea. Temperature is high and the dew point is low is the wrong answer. Temperature and dew point relatively close is the right answer. Those good students who understand that. If you have temperature and dew point that are close together, that means the cloud's going to form much lower on the mountain, and to be more opportunity then for that extra heat to get added as condensation going up the mountain. So if Seattle is socked in with rainy, very moist, 100% humidity, and that air is forced over the mountain on the downwind side, typically it's going to be much, much warmer than it is on the upwind side. Well, that's all our thoughts today on the adiabatic process. Thank you for attending.